Everyone can hear me all right? Yeah? Awesome. All right, so at the end of the last session, you learned that Viator's Rips pretty much starts to break down after dimension 2, right? So for instance, we went back, so I don't know if the rest of you finished the exercise, which is trying to get the right homological features. So this was the point cloud. And what you could do is you could readjust what the parameters were. So a good parameter was 4, but only on 100 points. And then you ended up getting something that looked like this. And then you could check out its homological features, and you get exactly the features you would expect. Yeah? A lot of people tried increasing the number of points, and they realized, oh, they don't have 5 hours to compute the whole Viator's Rips, right? So that was one of the biggest issues. Some of the other issues that they found was they realized when they plotted these points in high dimension, they were getting these really tiny H2 features, and they thought, yeah, this is a sphere, but it had 71 connected components because most of the points were completely disconnected, and they actually just got a tetrahedron void, which that's not correct either. So in many ways, TDA requires us to constantly check beyond just looking at the barcode. You can't just look at the barcode. You got to actually examine what are the cocycles, what are they doing. What's nice in low dimension is we can look at it, we can see what's going on, we can check and be thorough. But in low, let's do it. Let's see if we can get that feature. 0.5. That should be relatively quick to calculate. So they got one of these features, but really it only connects like a couple of things. They were able to get a tetrahedron. So the torus, impossible. You won't be able to do it. So now that necessitates the need to define more impressive filtrations. So if you open up the third notebook and quickly run everything, just to get things started. This is going to feel mostly like a lecture for the first about 40 minutes with a fun exercise at the very end. Question? I might be loading still. All right. But just watch the lecture for now, and if it still feels that way, ask me in about 40 minutes. Okay. So one of the first things we're going to find is higher order Voronoi diagrams. This is kind of an opaque definition when someone just first throws it at you, but it's relatively easy. The idea is I take some subset of points within my high dimensional space RD. And for every single one of those points, I define a Voronoi cell, which is defined as all of the sets of points that are immediately surrounding that cell that are closest to that chosen point. So, like I said, the definition is opaque until you see it. So here's an example. I have a bunch of points in two-dimensional space, and I selected 5 representative points. Why I chose 5? I just guessed 5. It was arbitrary. But now let's take a look at the first order Voronoi diagram, which represents all the points that are closest to each individual selected landmark point. So the blue region at the center are all the points that are closest to that center X. I have the green region, which are all of the points closest to that leftmost X. I have gray, which is all the points that are closest to that bottom X. I have that light blue, which is all the points that are closest to that rightmost X. And then I have brown, which is all the points that are closest to that topmost X. Does that make sense? That defines the first order Voronoi diagram, which represents just one order of information. But let's increase that. Let's generalize. So we can increase the order of information to the 2. So for instance, now, that topmost gray region, it's not just those points that are closest to the top X. It's now the closest points to the top X, second, the middle X, the center. And then you keep going. So you have that kind of lime green. I'm going to use a pointer. That lime green is closest most to that one, and then that one. The pink is closest most to this one, then this one. And then this purple is closest to this one, then this one. Do you see where I'm going with this? So we're introducing order relations. So we can do it a second time. Let's do it a third time. So now I got the gray is closest to this one, then this, and then I'm going to guess this one, and this one is closest to this one, then this one, then this one. This one is closest to this one, then this one, then this one. This one's closest to this one, then this one, and then maybe this one. And then it just keeps going. And then we can even do the fourth order. And we can even do the fifth order. At some point, you're going to exhaust your space, at least in lower dimensions. In higher dimension, this isn't the case. You can exhaustively create Voronoi diagrams, and you'll have all of the Voronoi diagrams for which you chose the landmark points. It's only in lower dimension that you see the degeneracy. But these are very powerful for a variety of reasons. For the first reason is we can define something called the alpha complex. We all love the alpha complex, right? The alpha complex is created on top of, some people call it the Delaunay complex. I don't like that. I like calling it the Delaunay triangulation. And that's because the Delaunay complex doesn't really give you access to the idea of a filtration. So the Delaunay triangulation is given a finite set L, which are my chosen landmark points. I take the nerve of that first order Voronoi diagram. So you can define a lot of things in terms of the nerve of a Voronoi diagram. And that's defined as the Delaunay triangulation. And it looks something like this. But some really important notes. When I'm only working in that first order Voronoi diagram, we can get the Delaunay triangulation by connecting two sites. So I can connect two of my Voronoi cells by a straight edge. So if we think of these two cells, there's a straight edge that connects them, and therefore I have the edge that interlocks whenever the two corresponding Voronoi regions share an edge. What does that mean? Well, when we're in lower dimension, that means that we have possible degeneracy constraints. So generically, the intersection of any four or more Voronoi regions is empty, right? Especially when you're in lower dimension. So three Voronoi regions may intersect in a point, which is then the endpoint of the three regions formed by taking the pairwise intersections. So you're only really likely you're going to get those one simplices, and you'll get those two simplices, and it's very unlikely that you'll get three simplices and beyond, which is one of the reasons why the alpha complex is so sparse. Moving on to the alpha complex, for every point in a given set S, we define the cover. So we define some supported balls, which are, we take every point X, we put a ball around it, and then we intersect that with all the points within our Voronoi cell. Visually, it looks something like this. Notice that we have a Voronoi cell, and we kind of cut it off at the radius. Again, we're defining complexes in terms of the nerve of something. And then we take the nerve, which is the intersection. I like defining filtrations very explicitly, so the filtration value for each simplex within the complex is defined as f on the simplex is equal to the minimum radius defined for the intersection of the ball. That is not empty. Make sense? Visually, it looks something I like this. I did steal this as well, and I didn't give a lot of credit. I'm so sorry. A lot of these come from Edelsbrunner's books, as well as Boissonat's topological and geometric information, or topological or inference on topology and geometry. Boissonat's book. Anyway, so this is an example where you start off very small, and you're slowly growing that very sparse representation, those sparse connections in between them. You're not ending up with things down here connecting with things up here, which was the problem of Viator's rips. Viator's rips always led to the complete click. That's a problem. When you have the complete click, you overload your system, and it gets too slow. Oh, are there questions? Oh, never mind. No questions. Okay. So, like I said, nothing interesting can be defined for higher dimensional simplices. So, We saw that we couldn't do the torus here. It was very sad and made all of us cry. So instead, now we have to reattempt the torus. So let's all run it on our computers, but if you don't want to run it, you can just watch. So start off with 10,000 points. That's right. Alpha complexes are incredibly strong and very fast, especially when they're in 2 and 3 dimensions. There's a fast algorithm that solves them that doesn't work when you get into higher dimension. Unfortunately, it gets very slow. So start off with 10,000 points in dimension 3. So that's what the d equals 3. And I have a torus of radius. The lower radius is 2 and the higher radius is 5. And then I calculate all of its random points, and I get something that looks like this. That familiar torus. So what I do is I take all those points, combine them together, and honestly, I let Goody do all of the work for me. I'm not doing any work here. I don't want to. The only work I'm doing is I'm defining some kind of maximal radius. So that means I have to choose, as a user, the maximal radius to calculate. Otherwise, I could overload the system too. But I have so many points. That I can really get away with choosing a really small radius because I know they're going to fill in really easily. So I choose something like r equals 0.5. Did I have to choose that? No. It's a choose your own adventure. And hopefully this adventure goes in a very good direction. Okay, so I calculate the alpha complex. I extract the simplex tree. I then calculate the persistence over a certain field. Remember, I choose coefficients, and I chose the coefficients too. And then I plotted. And notice what I get. I get this almost for free, right? That's the power of alpha complexes. It speeds so much computation with its sparse representation. And further, I'm not done there. I'm going to check myself. I'm going to make sure that visually it is what I want. So this is what I end up getting for visual representation. This is my torus. Does this look about right? Yeah? I think so. We all have this working on our computers as well? Yeah? Perfect. All right, so that's one type of filtration. It's a very powerful one. So note, computing higher dimensional data sets. My advisor, Eric Carlson, and I worked on developing a software package. It's called DensaTDA. It's on my GitHub, but we haven't officially released it yet. That calculates the alpha complex beyond 3 dimensions for these higher order Voronoi cells. So if you want to take a look, this is the original paper. The algorithm was conceived by him and his brother, John. So the 2 Carlson brothers. Yes, their dad is Gunnar Carlson. All right. So this is something that I worked on. This is based off of my advisor's paper, which is clicked right here. So if you really want to go read it, you can. So the idea is there are so many interesting filtrations that can be defined at any time, especially ones that are motivated by statistics. So effectively, the idea is a filtration should be thought of as a scalpel, right? And so, or any other tool that you can extend yourself. You can make it. And that scalpel, the way you cut, is how you construct your filtrations. So I construct this is one type of construction, and it's a sort of simpler construction compared to the paper. But the idea is, given some data points x, I can define some kind of function on the power set of x as a potential function. So, and this seems like a very strange thing. Like, why are you defining this idea of a power function or a potential function? I then take some landmark points and I define the filtered complex on those landmark points by taking intersections of the Voronoi cells with x, my data set, and then I define the filtration by taking the maximum value of some function over this. Oh, I did mean to define. Well, this automatically satisfies the constraint that. Remember, our requirement was for any subface within my complex and tau a subset, that implies that f of tau must be less than f of sigma. So you have to be able to provably say that for whatever function. So one function that for which this works is something as simple as the division over the cardinality, right? Seems very basic, right? But in fact, it yields tremendous results very quickly. So not only that, but it also has one advantage, a huge advantage over Viator's rips, in that immediately you see an upper bound, right? This function is automatically upper bounded by 1. And so you only have to calculate, you only have to calculate up to a radius of 1. That's something that automatically you don't have with Viator's rips unless you scale everything down. And even then, it gets squirrely in higher dimension, and you gotta maybe divide by like the square root of d or something. So to justify why this algorithm is powerful is, here is the dimension of the simplex, and this is the number of simplices that have to be considered taken to log, which means as Viator's rips is growing exponentially for this simplicial complex, you only have to consider at some point a constant number, which is the logarithm of the number of cells, logarithm of the number of data points. That's very powerful, right? That means we get virtually ease of computing in higher dimension. Alpha complex will actually be pretty much the same. The alpha complex actually technically still grows, because the alpha complex is not based off of the number of data points. It's based off the number of Voronoi cells. And technically those still can grow, but the alpha complex will shut down when you don't have an intersection, and that'll actually cut anything in between. So realistically, the alpha complex will be like probabilistically somewhere in between. Other questions? Yeah? Okay. So let's go ahead and run. Again, I take a lot of points. I'm going to have a radius of 1, same object, which is the torus. And what I do is I'm going to landmark. So the reason is that landmarking is very powerful. Typically what you want to do is when you landmark something, you want to use an epsilon net. I didn't have enough time to go over landmarking. That would have been another lecture if I had been given another lecture, but that's okay. But it's a wonderful area as well, because there's a lot of papers coming out about generating epsilon nets, generating covers of manifolds. I'm working on a paper with my advisor now on effectively covering high-dimensional spheres. And that's very powerful because you have to do it in a very special way, otherwise you have cursive dimensionality. So we calculate the simplex. It does take some time. That's why I had you run your computers beforehand. It takes about 4 minutes for this very basic construction. With only 100 landmark points, you think, wait, you only have 100 landmark points, and you think this is going to beat Viator's rips or the alpha complex? Yes. Yes, I do. Well, I say that, and then I got this. It looks like we had something die, and we had... I mean, I could probably rerun it. I don't feel like rerunning it now, but you get something that looks like this. This doesn't give it the full justice, doesn't do it full justice, but this is virtually what you end up with image-wise or visualization-wise. If I were to rerun it again, I think it would work. But I wanted to go through this quickly because, and this is true for anyone, oh, I don't want to show that just yet. This is true for anyone who's watching online. I want you all to participate as well. So the next part, and maybe you've seen it on your own computers, is a little competition. As like a final exam for coming to this wonderful Applied Topology school, which is I've given you 2 data sets, and I want you to use the tools that you learned in my class and in any other class. Paul's class, the stuff that he talked about as well, absolutely works, and I made sure it works in your environments too. So I know you don't have to pip anything, you don't have to install anything, it will already work. But you can take some of the work, and you have to be able to solve those data sets. But in the meantime, wait, I wanted to regenerate the set. Okay. While that's running, I'll talk about your final exam. Now that we have about 40 minutes or so, maybe a little more, 45 minutes for your final exam. So the idea is, you've all seen this probably when you were a child. It's what's that Pokemon? I thought it was interesting because it's a weird shape and you don't know what it is. And so the idea is you have to use TDA. You have to use the tools that you learned. Do you know how many years it's been since I actually learned? I was playing the card game, but I don't remember. Sorry. It's the coin battle. I don't know. Anyway, so the rules are you're not allowed to plot the manifolds. You're not allowed to. You can't use lower dimensional representations. You're not allowed. You are not allowed to look in the utils file. I'm sure you could probably look in there and figure out what the embedding I'm using. But you are allowed to use any of the tools from this course or others that you believe should work. Question? Well, that's why in the last session I had you pair up with somebody with a computer. Blank?
They need to pull.
Oh, yeah, you need to actually go and pull. So I said that at the very, yeah. So you're in the folder. You have to do git pull. Remember that?
They will encounter an issue with the if they do changes from yesterday. So they need to restore first. Git restore.
Oh. All right, git restore. Then dot.
And then git pull.
And then git pull. Yes. First restore and then pull. Restore dot and then pull. Make sense? Thank you for that. I appreciate it.
Yeah, because I encountered the same issue and I thought you.
I'm glad I fixed it though.
I'm generating the data set, so I am.
It takes a while.
Yeah.
All right. So for the next 40 minutes, what you're going to do is you're going to fix your computers to download the data set. And then what you're going to do is you're going to solve. So figure out what these are. Use the tools that you learn. You learn how to construct many different filtrations, and then you learn how to analyze it. Of course, you've got to really figure out, are you actually encompassing the data that you want? So next 40 minutes, go ahead. I'll come back in about 5 minutes before the end. And everyone at home also work on this too. Okay, 5, 4, 3, 2, 1. Okay. So before we go into the results, I want to talk about the philosophy of TDA because this is really what propels this field. TDA needs to be more statistically robust, just fundamentally. It has to be. Like Powell kind of talked about all the wonderful successes of TDA, and I've kind of spent the last 3 lectures kind of talking about the downsides, the sad, I wouldn't say the sad, the failures, but rooms for improvement. And so TDA, we'll call it challenges. And that's exactly what y'all just did. You did a TDA challenge. You were trying to figure out what these underlying manifolds were. So the first thing you did was what? You did the manifold hypothesis, which was you assumed that there is some underlying manifold that describes this higher dimensional thing, right? That hypothesis is an assumption. When you're given a data set, you assume that there is an underlying manifold. That's step number 1. Step number 2, you tried analyzing, oh God, that hurt my soul. You tried analyzing the data And you did a couple things. You tried to find homological features. Did anyone do anything else, possibly? So what you could also do are things like dimension estimation, which is exactly what was kind of discussed, or Catherine at least discussed in her talk, right? This idea that you can try and understand some kind of dimensionality that's underlying some space. In her case, it was a parameter space, but in our case, it could be our data set, right? This is a really big problem, right? Being able to understand the inherent dimensionality of data. So these are very powerful. And then, of course, there's visualization. I said, do not allowed. I know. You are allowed the visualization for the barcodes, but you aren't allowed to necessarily project anything down into lower dimensional space. So some of the things you noticed while you were working on it was you were getting these kind of barcodes that looked like, let's try and keep the colors consistent. So you got some H1s that kind of bounced up here, infinity. And then you got this weird, it could either happen in two ways. You can either get a mountain, and then you got all these features up here. What happens when you see this? This is true when in practice. In practice, when you see this, what does this suggest happened? The radius isn't enough. That's always true in practice. So in fact, you need to increase that radius in order to allow it to peak out. And then you might see some homological features up here. And then let's get I know I don't have a green, but what's going to happen is those H2s are also going to start appearing. And what you have to do is you have to let them peter out. And then you might get even higher dimensional stuff, right? So dimensionality does become an issue, right? You want to know the inherent dimensionality of your data to tell you how many dimensions or how many homology groups I'm actually going to calculate, right? This is all part of the process. I wanted you to go through the process at least once this workshop because you can tell it's hard. It's not easy, right? You can't just hope everything works out efficiently. So some of y'all tried guessing. A bunch of y'all guessed the Klein bottle. Yes, that is correct. And then one person actually said it, but you kind of said it in passing. This is the projective plane, RP2. Now, a lot of you did it using alpha complexes, which surprised me because I basically gave you my research poster, and I gave you the complex that calculates all of these groups. So if you were to visualize, you'd end up with the torus. Let's zoom in. If you were to visualize it, you'd end up with the wonderful the pinched torus. And when you think of the pinched torus, notice that I've colorized it by dimension. So you have the yellow kind of allowing the Klein bottle to go in on itself. So it goes in and then under and then over again. So that's the Klein bottle. Notice what the H0s are. The H0s, H1s, and H2. And then in F3, you get exactly the coefficients you should. And then this is a visualization. Same thing for the projective plane, right? You have this idea that you have all of these dimensions kind of intermixing. And if you were to plot, you would get the correct homological features for 111, and then it should just be 1. So it's a tough problem. This isn't easy. You can't just wing it. But I wanted you all to at least experience what it's like to be given a data set. You're trying to find out what it is. It's tough. And a lot of it is an art. You're picking complexes, you're picking filtrations that model your data well. And then you have to try and go through the process of figuring out, is this exactly what I'm looking for, or am I making a lot of assumptions? TDA is hard. Welcome. It's great. And now I certify you all as experts in TDA, the ones who participated, the ones who did their own thing. Well. Anyway, yeah, so that's it for my talk. Are there any other questions, concerns, comments?
Where can you go from here?
where can we go from here? Defining more interesting filtrations, because there's so much to be done about making them statistically robust, right? Viatorus rips is known for not being statistically robust, and you want to make sure that you define them well enough that you don't end up with issues like, if I have a static ring, how can I ensure that that static ring always stays the same, right? These are constantly persistent features, and if you use Viatorus rips, for instance, it closes up into a complete click. That's not useful. So the idea is you want to make them more statistically robust, especially in higher dimensions. You also want to be able to apply to different kinds of data, like categorical data, time series. All of these are wonderful domains that are absolutely worth exploring because they do merit their own attention. So, any other questions? Yes. For what? How do you keep learning about? I mean, a lot of it is there's so many wonderful conferences or seminars. You have the Geotopic seminar that happens, I think, every 10 days or something like that. You also have the Applied Algebraic Topology Research Network that Henry Adams tends to kind of run. So you have a lot of different people who are making sure that they publish on TDA. And coming to conferences like this is probably the best way. So participating, I know there's going to be another Applied Topology school next year. I may or may not be there. I don't know. Maybe I'll give another data challenge. Oh, sure. Hey. They have AATRN, the N, the Applied Algebraic Topology Research Network. You also have Geotopa. No, what? A what? Okay. Well, we'll have another one. More questions? Yes. Yes. Yeah. That's right. Oh, absolutely, that does affect it. So you could end up with oversampling in certain parts. You could end up with effectively you've left entire swaths of points open. So that's why you need more statistically robust filtrations. It gets hard. For instance, something that I feel like this should be relatively easy, and I've been thinking about it, which is like, say you have a torus, but with just a hole in it. I mean, the hole exists. The hole is there. I'm telling you the hole is there. What would TDA give you? TDA would say, well, you have Betty 0 of 1, Betty 1 of, I think you only get 1, and then Betty 2 of 0. Which, that's not great. Like that's horrible. Like you want these Betty numbers to tell you it's a torus, or at least tell you something else. So maybe there's some way of statistically saying something about that little hole. That's like a little boo-boo on the torus that you want to put a Band-Aid on. Mathematically, you want a Band-Aid. Questions?
The next question is you can with learning
Can I take can I color it in, or what do you mean?
The coloring red is connected with the color black, for example.
I mean, I colored it so I colored it originally on this so you could see which ones are the disconnected components. These are all connected, right? That's why they're all the same vertices, all the same color on the vertices. Is that what you're asking? Yeah. Okay. Any last questions? Okay, cool. Well, thank you all.
So let's thank Greg again for this series of 3 really awesome introductions to this area. I think it's just a really great resource. So thank you.